Hello student to the foundation of classical electrodynamics course. So, under module 2 today we have lecture number 31 and in last couple of classes we discussed about the electrostatic energy and Green's reciprocity theorem etc. So, today we will going to continue with this concept of electrostatic energy and try to calculate few problems where the charge distribution is given to you. So, today we have class number 31. So, before going to the calculation, so let us understand one thing, that the electrostatic total energy, the total electrostatic energy is a non-negative quantity. You need to show that actually that this is non-negative, and there are ways to show it. So, as per our definition, this is half of rho phi dV. Okay. Now, we are going to use we will try to show another another way these things. So, the divergence of E is rho by epsilon 0, that we know, and that leads to the value of the rho in terms of E, and that is rho equal to epsilon 0 and multiplied by divergence of E. That thing I should plug in this equation. So, then we get half, then integration rho, in place of rho I just write it epsilon 0, then the divergence of E, that part, and then rest part is as usual phi dV. Now, I am going to use a vector identity. So, the vector identity is the gradient of a scalar field multiplied by the vector field. This is a very important, and that we know that this is the phi, the scalar field, multiplied by the divergence of the vector field, and then plus the vector field dot the gradient of the scalar field, that we know. So, I can from here I can see this term here, gradient of vector field multiplied by, so this quantity is sitting here. So, I replace this with other two. So, that means phi multiplied by E is simply minus that thing I replace, then I will simply have it is half integration, then I can have this entire quantity. So, epsilon 0 then in the bracket I should have this quantity whatever is written here. So, let me do it in different colors. So, it should be this. Bracket close and then dv. Okay, this is the term, and so I can divide this into two part. So, half integration of say epsilon 0, I can take it outside, and then the other term is this. When phi e dv and then minus of epsilon 0 divided by 2, then integration of this term. Here I am having this quantity which is divergence of phi, gradient of phi. So, the gradient of phi is simply the minus of the electric field, minus of gradient of phi is this quantity. So, that if I put, then I should have a plus sign and simply E dot E here with dV. Now, this is if I make this is over volume integral. So, I can make it a surface integral, closed surface integral according to the divergence rule. So, it is phi E over the surface ds. On the other hand, in the right hand side, other term is epsilon 0 divided by 2 integration of simply E square dV, because it is E dot d. Now, if you look carefully this term, then for a point charge the phi varies as 1 by r, E varies as 1 by r square, and ds, the surface element for polar coordinate, that should varies as r square. So, that means if I take an infinitely large or very large surface, then the contribution of these things will be 0. The contribution of this part will be 0. So, that means the W e is simply equal to epsilon 0 by 2 integration of mod of E square or E square and then dV, and that quantity is obviously greater than equal to 0. So, that basically proves that the electrostatic energy is a non-negative quantity. Okay. So, this is one way to show that, and also this expression that we derived from here, that its value is epsilon 0 divided by 2 E square, it should be useful, and we will going to use that maybe in future calculations. Okay. After that, for electrostatic energy for different system, if I whatever the information we have so far, if I write it down. So, the set of energy of the energy of the set of field set of discrete charges set of charges is W e is equal to Q I Q j divided by 4 pi epsilon 0, then R I j. R I j is nothing but the distance between these two. So, in many places it is written in this way. So, that is why I am writing. So, R I j is mod of R I minus R j, and this is for all pairs. This is for all pairs. Okay, so that we already discussed. So today we are going to make a problem with that. We will show one problem where we are going to use this expression. So for distribution of charge for a distribution of charge, what we have is this quantity. This is half integration of rho phi dV, and that quantity we just before calculate. This is epsilon 0 divided by 2 integration of mod of E square dV or E square dV or E dot E dV over the volume integral, that is the value. Third is for spherical cell. Spherical cell, we will show that the W e is half of q square, sorry, this is not q2, this is q square divided by 4 pi a epsilon 0 a, where a is the radius of this cell, and finally the sphere of constant charge density that value is 3 by 5 and then q square divided by 4 pi epsilon 0 a. That is the value, I just write it here. So, now one by one we will going to see. The first thing is the example 1. So, now first I will show example 1, and that is the point charge. The want to find out the, so this is the distribution of the charge that is given. So, one charge is sitting here, say this is q2, another charge is sitting here, say q3, and another charge is sitting in the origin. Say q1. So, this distance, so the location of these points are given. So, this is q1. So, the location I write here, the coordinate, this is 0 0 0. The coordinate of this point is, say this is, if this is my x axis, this is my y axis and this is my z axis, then it is 0 0 1, and this the coordinate of this point q3 is over x axis. So, this is 1 0 0. So, the distance between these 2 points I can calculate easily, which we may be requiring, and that is root over of 2. Now, the question is, if I am having this 3 charge distribution q1, q2 and q3, then what should be the energy? Now, this I know, right. So, this is the formula for discrete charge, all pair and then qi qj divided by 4 pi epsilon 0 and then r ij. This is the formula we know. So, we are going to use that here. If we use the, I should have 3 pairs. One pair is q1 q2, another pair is q2 q3, and another pair is q3 q1. So, the distance between these 2 pairs q1 and q2, I can also find out q1 and q2, the distance is 1. For q1 q3, the distance is again 1, and for q3 q2 the distance is root over of 2. This is root over of 2, and the distance between these 3 q3. So, I should write this is 1 2. The pen is not working properly. This is 1 2, this is 2 3, and this is 3 1. For 3 1, this is 1. Now, I will just simply use the formula, and if I do, then I simply get 1 by 4 pi epsilon 0, this is my W E, 1 by 4 pi epsilon 0, then q1 q2 divided by 1 plus q2 q3 divided by root over of 2. So, this is 1 and plus q3 q1 divided by 1. So, that should be my answer. Now, in the problem, the value of q1 q2 q3 can also be given, and I am just putting the value here. Suppose q1 is given as minus of 1 nanocoulomb, q2 is given, I am just putting some arbitrary values, q2 is say 4 nanocoulomb and q3 is say 3 nanocoulomb. So, these are the value of the point charge, and if you this value is given and this is the distribution that is given. So, you can calculate what should be the total energy of this system. Just put the value of q1, q2, q3 here in this equation and you will get the result. Okay. Now, let us go to another problem, example 2. This example is try to find out the uniformly. So, energy of the uniformly charged spherical cell. This is a very standard problem and most of the textbook it is given. For example, in the Griffiths you will find this problem. Well, I am just trying to do this. So, this is the spherical cell with radius A. We already had this expression. I just wrote it just before I wrote this, that the value should be half of q square 4 pi epsilon 0 A here. I have already mentioned this. So, now I am going to show it meticulously how to calculate. So, the electric field we know for this cell at the point r greater than A is simply using the Gauss's law, it should be q divided by, because q is the total charge, 4 pi epsilon 0 and then unit vector r by r square, that should be the value. Okay. And for r less than A, this value is 0. So, there will be no electric field inside this cell which is charged. So, the energy, I know the expression E square dV. So, I just need to calculate this. So, dV here is a spherical cell. So, dV should be the volume element due to the coordinate, the spherical polar coordinate, it is r square sin theta d theta d phi and dr. This is the volume element we know. Now, the E value is known, is over here. So, that means the energy should be, so whatever the electrostatic energy we have from the infinity to A. So, that means here and then I have, so I have E square. So, I have q square divided by 4 pi epsilon 0 square, and then I need to have this integration. The integration inside I should have 1 by r to the power 4 and then r square dr, and then I have 0 to 2 pi d phi and 0 to pi sin theta d theta. So, we know that this contribution always comes up to be 4 pi. So, that thing I am going to use here, I am going to put here. So, this quantity simply becomes epsilon 0 by 2, then whatever we had, q divided by 4 pi epsilon 0 and the square of that quantity which we had already here, and then this 4 pi will come out from the integration, and we have the integration r from A to infinity 1 by r square and dr. So, this simply gives us q square 4 pi, 4 pi will cancel out, 1 epsilon will cancel out. So, it should be q square by 2, then 1 by 4 pi epsilon 0, and then this quantity is minus 1 by r, then A to infinity. So, now if I do the integration, it should be simply q square divided by 2 and then 1 by 4 pi epsilon 0, and then this quantity is 1 by A. So, that is the expression, precisely that is the expression we are looking for. So, this will another way you can also do, and that is this is another way. This quantity we know that for surface charge distribution I can write it as sigma and ds. This is the charge and then phi, the potential, okay, because W E for discrete charge I just use that concept that it is half and then this is sum over q I phi I integration over I 1 to n. This is for discrete charge, and now if we have a continuous charge distribution, so this q I charge can be represented as the surface charge density sigma over ds. Okay. Now this phi you know, right, phi is the potential and that value is q divided by 4 pi epsilon 0 A, which is the potential on the surface of the cell. This quantity is nothing but the potential on the surface of the cell. So, the potential is known. So, I just simply use that because this does not depend on the integration. So, simply I have half and this quantity is q divided by 4 pi epsilon 0 and A, and then I have integration sigma ds. Now, this sigma ds is nothing but the total charge, right. This is the total charge. So, I can have half of q square divided by 4 pi epsilon 0 and A, which is the same result that we had in the previous calculation, the same thing in a different way, q square divided by 4 pi epsilon 0 multiplied by A and then multiplied by half. Okay. Now, finally, I will like to do the problem. This is for spherical cell, and now I will have for this is example say example 3. So, now we calculate the energy, electrostatic energy for a charged sphere, for a charged sphere. So, the problem previously was cell. So, that means I simply have a very tiny cell here like this. But now it is a sphere. Now it is a sphere. So it is simply a sphere. Okay. So, the energy of the sphere is, if you calculate, so it is simply the work done in gathering the charges together from the infinity. So, I have a charge here. So, I will gradually bring this charge to form this sphere, and in order to do that I need to do some work, and that work should be equivalent to the electrostatic energy. So, for example, if bring you the first charge, then there is nothing here, but when you put the second piece of charge, then it will experience some kind of field due to the charge that is already there, and so on. This process will go on, and you need to do some work to bring more and more charges to form this sphere. So, exploiting that idea, we will calculate. So, that means this is the amount of charge dq I bring from infinity and then gradually form this sphere. So, let us make a cut here and make a cell here. So, that is the region I want to fill with the charges dq. So, this is the region of my interest. So, I bring the charge here to gradually build this sphere, but let us start with this. So, this is the region first we are going to build. So, how I write mathematically? So, mathematically is d w omega, this is the amount of energy that. So, the amount of work done, this is basically the amount of work done in bringing the charge dq, this charge, bringing the charge dq to a charge sphere of charge say. So, this is now R, and already this amount of charge is there, and this is the radius A, and already this charge is there. So, this charge say QR, which is already form a sphere of of radius R, of charge QR and radius R. So, this radius is gradually increasing when I bring the charge from infinity. So, this is A. So, okay. So, first we calculate what is the amount of the charge you already have. So, this is I am saying QR, right. So, what is the charge already it has. So, QR is simply 4/3 pi r cube, and since it is uniform charge distribution, so rho is the charge density. So, the amount of work that we do is simply the potential that it is generating, that is QR divided by 4 pi epsilon 0 r, and the amount of charge I bring, right, dq. QR is already there. So, I have 4 by 3 pi r cube and then rho divided by 4 pi epsilon 0 and r and dq. Okay. So, then dq is the charge that build up the sphere with radius r2. So, dq is a charge. So, dq is the amount of charge, the charge that builds the sphere with radius r to r plus dr. So, just it increased, dq is the amount of charge that increases the radius r to dr. So, what is dq then? dq in terms of rho I can calculate, this is simply 4 pi r square and then dr and rho, that is the region, this region, the amount of charge in this region. Having radius r to dr. So, this is dr and this is r. Okay. So, this from here to here it is dr. Okay. So, now I have dq. So, dw E is simply 4 by 3, whatever we had already, 4 by 3 pi r cube, then rho divided by 4 pi epsilon 0 r, and in place of dq I simply write 4 pi r square dr and then rho. So, it seems that 4 pi will going to cancel out and few more terms will cancel out. So, 1 r and 1 r square will cancel out, epsilon 0 remains same. So, eventually I have 4 pi here and then divided by 3 epsilon 0 and then rho square should be here, and then I have r to the power 4 dr, that should be my. So, now I need to create the entire sphere. So, that means my WE, the total, that is the total energy, and that should be integration of the total thing with the limit 0 to a, because I am forming the sphere of this radius from 0 to a radius. So, then I just simply integrate it. So, it is 4 pi rho square divided by 3 epsilon 0, this is a constant, and then I should have r to the power 4 0 to a dr, and that quantity is r to the power 5 divided by 5. So, simply we have 4 pi rho square divided by 15 epsilon 0 and then a to the power 5, okay, that value. Now, I can return back because the total charge q is there. So, I need to just change this rho in terms of q. So, q is the total charge and that is 4 by 3 and then pi a cube rho. So, from here I can write rho is simply equals to simply equals to 3 q divided by 4 pi 3 q divided by 4 pi and then a cube, that is the value of the rho in terms of q, and now I put this rho here in this equation, and if I do, then WE will be simply 4 divided by 15 epsilon 0 and we have rho square. So, that means the square of this quantity. So, that becomes 9 q square divided by 16 pi square, then a to the power of 6 and already a to the power 5 is sitting here. So, few terms will cancel out, for example 4 and this here, and then 3, and so I should have 3 divided by 5 here, and then q square should be here, divided by 1 4 will cancel out, and another, okay. So, I should have a pi here also, yeah, 4 pi here also, so I missed that. So, that pi will also cancel out. So, simply I have 4 pi epsilon 0 and then A. So, that should be the value of the potential energy of a solid sphere having the charge density rho and the total charge q. In terms of charge density we already calculated, but in terms of total charge it should be this quantity. So, that again we already wrote it earlier, that this should be in a listed way, that what should be the energy, I think here we wrote it, and then gradually here. So, this is the value I wrote earlier. So, that again we meticulously calculate and check. Well, today I do not have much time to discuss more, so I would like to conclude my class here. So, in the next class maybe we will start a new topic like the multipole expansion and all these things. When we have a charge distribution, then what should be the potential at a long distance, that we discuss, and that potential can be divided into few terms which we call the multipoles. So, that we discuss and do few problems also. So, thank you very much for your attention and see you in the next class.